Here for day 2 for the short-term training program on FEA. We have Dr. M.S. Alphin with us, who is the Associate Professor, Sri Sivasubramaniam Nadar College of Engineering, Chennai. Dr. M.S. Alphin received doctoral degree PhD from National Institute of Technology, Tiruchirappalli, under the Department of Mechanical Engineering in the area of biodynamic vibration. He completed Master of Engineering and Bachelor of Engineering degree from the College of Engineering, Guindy, Chennai, and University of Madras, respectively. He has totally teaching and research experience of 17 years. Dr. M.S. Alphin research interests are in vibration, product design, human factors in engineering and design, automobile, and biomechanics. He has engaged in the real-time industrial consultancy for design vibration problems and currently a principal investigator for DST project worth 22 lakhs. He has successfully organized FDP, conference, and workshops worth 50 lakhs. He attained awards such as Best Faculty Award 2 times for teaching excellence in 2015 to 16 and 2017 to 18 from the management of SSN institutions. Best Paper Award in SimHealth 17, Symbiosis University, and for Best All-Round Abilities. He has 25 international journals, 2 books, and 19 international conference papers to his credit. Dr. Alphin has participated in the International Congress on Sound and Vibration, organized by International Institute of Acoustics and Vibration at Thailand, and AHFE 2019 at Washington, D.C., USA, with SSN Trust. He is a reviewer for revered international journals in his area of interest. 2 PhDs are awarded under his supervision in Anna University. Currently, 6 scholars of Anna University are working under his supervision. He is also serving as resource person, invited guest speaker, and conference session chair in reputed institutions. He teaches kinematics of machinery, dynamics of machinery, machine design, engineering mechanics, machine drawing, engineering graphics, FEA for BE BTech, and computer application and design, computer graphics, mechanical vibration, human factors, and product design for ME MTech. He has also developed e-learning content and tutorial sessions for all the subjects he is teaching. And I'm very proud that he was my professor when I studied in SRM University. So welcome you, sir. Over to you, sir.
Thank you, Mr. Amos. Nice to be with you and the gathering. And it's a good opportunity for me to be with you and to discuss the subject in this STTP program, and which is well organized and well planned. I welcome you all the delegates for the event too, and I hand over to Mr. Amos and for the next proceedings. Shall I share the presentation and start the session, Mr. Amos?
Yes, sir. Yes, sir. So the session will be on FEM model, formulation of FEM modeling using weighted residual method and variational method. Thank you, sir.
Yeah. So hope you are able to see my screen.
Yes, sir. Clear, sir.
Yes. So today, I think yesterday professor has given a wide introduction about the finite element analysis and its application and the techniques in depth. And today we are going to see about the finite element formulation. So this is the backbone of the finite element methods that we are seeing in an advanced form of engineering now. Finite element formulation is functioning. Mathematics is a background. So mathematics and partial differentiation can be utilized for solving many number of real-time problems in engineering. That is what has improvised as a finite element methods in current day problem, and this has been programmed, and it has been programmed in the finite element package, and we are able to use it as an end user and solve the problem of the real-time cases. So any engineering problem can be represented by partial differential equation. That is, for example, the Laplace or Poisson equation can be used to solve seepage, ground seepage problem, torsion of bar, heat flow, etc. So the method of finding approximate solution of differential equation, actually we create a differential approximate solution using differential equation within a domain, and then we formulate it for a proper boundary. So we always solve the problem for a particular domain and then formulate it for the entire boundary of the problem. So if you take a domain will have a field variable. For each case of problem, the field variable varies. For example, in a fluidic problem, field variable is different. Center material problem, field variable is different. So based on it, we use the differential equation and boundary condition to satisfy for a domain and to find the solution. So for this, we use weighted residual method. So weighted residual method is the first and most powerful way of finding approximate solution by using the differential equation. So Galeckin's weighted residual, in Galeckin's method, here we are using piecewise trial solution. That is, we are devising the entire domain into small domain. We give trial functions which satisfy the domains in a piecewise, so that the approximation is more near to the actual answer. So the flow in which we proceed the mathematical formulation to get the solution is, we formulate a trial function. For any devised problem, we formulate a trial function and we devise the trial solution so that it covers the entire domain, and then to make it more precise, we introduce a weak form in the problem. So now we are going to see how to solve a weighted residual method problem. So here you can see this is a trial solution we have taken for a problem, a normal problem that we are going to consider. This we say it as a single continuous trial solution. So this is the polynomial solution that we use for a general case, but not all the case we are going to use the trial solution. In some cases where the boundary conditions are more, or some thermal or heat transfer problem, then that time we are forced to use a trigonometrical function. But in general cases, many problems we are using this kind of polynomial function as a trial solution. So what we do is we assume a trial polynomial solution trial function for a particular or a domain problem, and then we equate the residue to 0. We find out the values of the unknowns in the polynomial, and then equate the residue in the differential equation we formulate to 0. So for that, we should know the value of the unknowns in the polynomial. When you know the value of the unknowns, we could zero down the domain residue. When you zero down the domain residue, we may get the accurate result. So it is not possible every time to go with the domain and boundary residue. If you are going with boundary residue also, then it is computed as a boundary element method. So, but in normal cases, we always deal with our domain alone. So generally domain means we have a differential equation which satisfy the particular condition and the boundary condition, which is applicable to the particular domain. So that is what we are going to do with respect to weighted residual method, and we are going to solve few problems to validate this weighted residual method. So this is a problem in a strength of material, a rod subjected to axial load. So here is we have a rod, and this rod is subjected to axial load. You can see the arrow mark showing the axial load, and field variable in this strength of material problem is Q naught, and X is the displacement. So L is the length of the rod. So L increases from here to here, and this is the condition. For this, we devise the governing equation. So deformation of bond, we take the governing equation as t squared u by dx squared plus q naught is equal to 0. So this is the governing equation, and we devise the boundary condition based on the problem. So u of 0 is equal to 0. At x is equal to 0, at this point, there is no displacement, 0. Okay. So du by dx at x is equal to L is equal to 0. Okay. So du by dx at x is equal to L. So it is a differential. So here the value of x is substituted by L, because the L, with respect to L only, we have to compute the displacement pattern, how it is going. So du by dx of x is equal to L, 0. So we are taking the trial solution here. As per the weighted residual method, we take the trial solution. So the trial solution, we take it as a C naught plus C1x plus C2x squared. So this is a polynomial function. We have taken this polynomial function as a trial solution. C0, C1, C2. These are the constant that we have to identify. For identifying these constant values, we have to find out the value of these constant values. So already the boundary for the domain is already designed. So here it means x is equal to 0, u is equal to 0. So du by or the dx value, we put x is equal to L. That is what it means. So here also we put x is equal to 0. When we put x is equal to 0, C naught will become 0. That is what we got. And when you put x is equal to 0, this will become 0, and this also will become 0. So C naught will become, this value of this constant is found out by the boundary condition 1. The boundary condition, using this boundary condition, we have found out the value of C naught. And we can utilize the second boundary condition. We are going to utilize the second boundary condition. What is the second boundary condition? Du by dx of x is equal to L is equal to 0. So you differentiate this. So du by dx is C naught is a constant, so it will be 0. C1x du by dx of C1x will be C1x differential of x is 1. So C2 into 2x squared. This is what you will get. Okay. So as per the boundary condition, du by dx of when x is equal to L is equal to 0, that is what it means. So instead of x, we are going to put a L. Instead of x, we are going to put L as per the boundary condition. Instead of x, we are going to put L. So the equation will become C1 plus 2C2L square. Sorry, this x square is not there. So since this is 0 as per the condition, this should be 0, 0. So C1 will be minus 2C2L. This is what we are getting it here. This is what we are getting it here. C1 is equal to minus 2C2L. So using the second boundary condition, we are able to get the value of C1 also, C0 and C1. Now C2 is the only variable, this one that is there. So now the trial solution is U of x is equal to C2 x squared minus 2L x squared. Substituting the value of C0 and C1 here, we are getting this. So this is a one parameter. So we have only one parameter here. So we say it as a one parameter solution. So now we take the domain residue. Domain residue is taken from the governing equation. So here itself we have got this AE in this question. We have to find out. AE is missing here. So E squared u by dx squared. We differentiate the trial solution twice, and we will get 2C2. Okay. So we'll differentiate the trial solutions. Trial solution we know C0 plus C1x plus C2x squared. So differentiated twice, that generally we get this d squared u by dx squared. This is u. So d squared u by dx squared, then we get 2C2. That is what we are putting it here in the value here. So we got this. So this is the domain residue. Domain residue we're getting. So we have to minimize the residue. So for minimizing the residue, we have to equate the residue to 0. So when we equate the residue to 0, we will get the value of C2 also. We will get the value of C2 also. So now we got the value of C2 also. So residue is 0. So AU 2C2 plus Q0 is equal to 0. C2 is equal to. So that is what we got. AE 2C2 plus Q0 is equal to 0. So C2 is what we are getting it here. So now we have equated the residue completely to 0 because we got the value of all the constants. So the final solution, this is the final solution we are getting it. So this is the final solution we are getting it. So we have found out all the values in the trial solution, C0, C1 and C3. So we can substitute in this equation. This is a trial solution. Even we can substitute it there, we'll get the same answer. So already here we have substituted the value of C1 and C2. So this is the reduced one. So directly we can substitute the value of C2 here to get the final solution. If you substitute the values, all the three values here also, you will get the same solution, no problem. Now already we have reduced it because we have substituted based on the first and second boundary condition. We have reduced the trial function to this level. So this is a solution for the problem. So we could get the displacement vector to different points by using this formula. So thus this differential equation is paved the way to solve the problem, problem and find out the solution and parametrically analyze the solution of the problem wherever required. So we are going in for the next problem. for this is a problem. So this is a fluid mechanics problem. So laminar flow on an inclined surface. The laminar flow in the inclined surface. You can see the boundary conditions in the problem. So this is showing the gravity because this is inclined, this surface is inclined, and showing the laminar flow here. And here V of x field variable and the direction of the vector is shown. So we take the governing equation or the fully developed steady state laminar flow of the Newtonian viscous fluid on an inclined flat surface. So this can be given in this way because you know the Newtonian flow, viscous flow, that is a steady state laminar flow, will be governed by the shear stress and slip in the flow. So based on that, we devise this. So you know, nu is a coefficient of viscosity. This is a coefficient of viscosity, and v is the fluid velocity, and the rho is the density, and g is the acceleration due to gravity, and then the theta, showing the inclination. So based on this, we have devised the governing differential equation for this problem, and we are going to find the solution for this, and by assuming the trial solution and finding the residue in the solution. So the boundary conditions of within this domain, we are defining the boundary condition. Since we have to achieve zero shear stress, so dV by dx x is equal to 0. So v, velocity at L is equal to 0. That shows that there is no slip in the laminar flow. So velocity distribution, we are going to find out the velocity distribution using the weighted residual method. So our aim is to find out the velocity distribution in this problem using weighted residual method. So we have got the boundary conditions and the general equation for the differential equation for the problem as well. So our duty is to assume a trial solution. So as usual, in this case too, we will assume a polynomial trial function. So the polynomial trial function. So we can also be, since the boundary condition, here we have got two degrees. So we will take three constant polynomial solution. So C0 plus C1x plus 3x square. This is the trial solution. So when you differentiate it, we get C1 plus 2C2x. This is the dV by dx. Now we can apply the boundary condition. So what are the boundary condition? One is dV by dx x is equal to 0. So dV by dx x is equal to 0. So when you do that, dV by dx we got this, x is equal to 0. So when you put x is equal to 0 in this case, so this will become 0. So C1 will be equal to 0. That is what we got here. That is what we are getting here. C1 is equal to 0. So C0 value, C1 is equal to 0. Substitute here. So L is equal to 0. So VL is equal to 0. So C0. So actually, the second boundary condition is VL L is equal to 0. So I will put C plus C1L plus C2 L square is equal to 0. That is what it means based on the second boundary condition. So now C1 is equal to 0. So this will be 0. So now C0 will be equal to minus C2 L square. This is the second boundary condition. Based on the second boundary condition, we have got this one. Second boundary condition. Based on the second boundary condition. This is based on first boundary condition. dv by dx is the first boundary condition. First boundary condition is dv by dx x is equal to 0. Okay, just I am saying this. First boundary condition and second boundary condition. Okay, so now based on that, we could find out the solution for the solution in the trial solution. But this solution again contain a constant c. C2 is there. So this constant, this value of C2 can be in the trial solution can be found out only by making the residue, domain residue. So domain residue is always taken from this equation, governing equation. So we take the domain residue from the governing equation. So domain residue is nu. We know it is nu into d squared v by dx squared. We know the value of d squared v by dx squared, so we can substitute it. D squared v by dx squared. Okay, so v is c0 plus c1x plus c2x squared. So d squared v by dx squared will be 2c2. So that is what we are substituting it here from the general equation. From the general equation, we substitute the value of d squared v by dx squared. So plus rho d cos theta. So we can equate the domain residue to 0 now. So this is the residue. This is therefore it is set to 0. The residue is set to 0. So when this residue is set to 0, we are moving near to the closer solution. So it is set to 0. We are able to find out the value of C2. We are able to find out the value of C2. C2. Now substitute this C2 value in your trial solution. As I said, this is a trial solution. We can substitute it here. We have already linked this to this by substituting the boundary condition. So directly we will substitute here, and this is the exact solution. We made the residue to 0, so this will give you the exact solution for this problem. Okay, so that's this exact solution. So when it is a problem is less boundary conditions, domains are defined, then we are able to find out the solution. Mathematics playing a way for it. But when you have more number of domains, domain is big. The boundary has a lot of domain. Then in that case, the problem become complicated. So that's why we require heavy computational programming is required. So we'll go for the next problem. It is on the cantilever beam under uniformly distributed load. This is a cantilever beam, uniformly distributed, and here also the field variable is Q0. Field variable is Q0, and there are four boundary conditions. Four boundary conditions here. Let's see. V of 0 is 0, dv by dx of 0 is equal to 0, double differential of v when the value of v is L is equal to 0, triple differential of v when the value of v is L is equal to 0. That is what defined. So this is a general equation for uniformly distributed load. to cantilever beam. So first two boundary condition, it implies zero displacement at the fixed end. Uh, since v of x is equal to 0, v is equal to 0. So these first two gives zero displacement at this edge, fixed end, and the last two, zero bending and shear force at the free end. So shear force. So that's why we use a double line triple diffraction. So we assume we are aiming for zero bending and shear force at the free end. That's why we assume the second and third and fourth boundary condition. So since this domain is considered to have more boundary condition, we have to use a lengthier polynomial solution than the previous one. So v of x is equal to c0 plus c1x plus c2x squared plus c3x cubed plus c power 4 x power 4. So this is a polynomial trial solution that we assume for this problem, and we start doing the same procedure to find out the exact solution. So boundary condition is known. So boundary condition v of 0 is equal to 0, the differential of v 0 is equal to 0. So using this, if you put x is equal to 0 in this case, all this will become 0. So it implies it will give the value c0 is equal to 0. So differentiate it. In that case, you get c2 is equal to 0. C2 is equal to 0. In this case, differential case, C2 is equal to 0. How is this will become 0? So C2, we are getting 0. So we have substituted first two boundary condition, and so other boundary conditions we assume x is equal to L in the cases. So if we put x is equal to L, that is differentiated twice, d squared v by ds squared, d cube v by ds squared, and for x we put L value. So differentiate twice. So we are getting it c0 plus c1x plus c2x squared plus c3x power 4. So first if we differentiate, we'll get c1 plus 2c2x plus 4c3x cubed. So again if we differentiate 2c2x, so 2c2 plus 4 into 3, that is 12. So by this we could find out we substitute the value of L in the place of x we substitute the value of L. Instead of x, substitute the value of L here, and we know the value of C0 and C1 in all the cases. We substitute it. So in that case we will get this C2 I missed one parameter, that's why. C3x3 plus C4 x power 4. So so 3c3 x squared plus 4c4 x cubed. So this is dv by dx, d squared v by dx, dqv by dx squared. We should find out dx cube. So 2c2 plus 6 c3 so we use this differential and we substitute the value of x in this, and we are able to find out the and we instead of x, in the place of x we substitute L value, and we could all so now as we have found out the value of C3, C2, C3 and C0, C1, C2 also we found out by the first two boundary condition, and so we got this. Now our problem is to find the solution we should know the value of C4 only. So we take the residue is what taken from this this we take this as a residue. Now we know the value of d power 4 v by dx for 4. So already d up to the triple integrated differentiation we are done. When you do the fourth differentiation, we get 24 c4. So d power 4 v by dx power 4, you get 24 c4. So using this we rewrite the equation. If you rewrite the first equation, ei is 24 c4 we introduce here. So minus q naught, this is the residue which is coming from the initial differential equation, and we substitute the value, find out the value of c4. When we put residue to 0, we could find out the value of, we are putting residue to 0, so we are able to find out the value of c4. Substitute the value of c4 in the equation. In the trial solution we have got, this is a trial solution. So this c4 value is what we are waiting for. Using the residue, we got the c4 value. Equating the residue to 0, we got the c4 value and substitute. And this is the solution we have got. Solution we have got for the problem. Okay. So cantilever beam under the load, we are able to find out the condition, assuming the 0 displacement at one end, and no shear and bending on the other side. This is a solution. This is a parametric solution we are getting. So next, this is a beam problem. This has got a lot of conditions. The boundary conditions. We have to satisfy many boundary conditions here, and in such cases, it will be beneficial to use a trigonometrical trial function. It is a benefit to use a trigonometrical trial function. Trigonometrical trial function instead of a polynomial function. Yes, sometimes polynomial function also can be used to find the solution, but when you have more constraints, it's better to use a trigonometrical function. So this will give you a solution very near to the actual solution. So here we are going to use the trigonometrical trial solution. So for this problem. So this is the condition boundary, that is a differential equation for the problem. The same field element is Q naught and the length of the beam is L, and EI d power 4 V dx power 4 minus Q naught is equal to 0. So the boundary conditions are this. This is a boundary condition pertaining to this point. Boundary condition 1 and 2 are pertaining to this point, and 3 and 4 are pertaining to the length L. Yeah. So this boundary conditions are constraints that is given to the problem for the both the sides of the beam. So we assume the trial solution. So here as I told you earlier, instead of a polynomial trial solution, we are going to use a trigonometric trial solution. The trial solution is C1 sine Ix by L. So this is a trial solution we are assuming. So the domain residue will be, we have to differentiate this 4 times. So first differentiate, when you differentiate sine of angle, it becomes cos, again sine cos, then sine, then again it will become, when you differentiate the 4th time, again you will get the sine. 4th time, again you will get the, because d power 4 by dx power 4. So again you will get a sine pi x by 2, but this pi by L will repeat again and again. Since this is a constant which is multiplying the variable, so this will repeat again and again. So it will become power 4. Okay. So that is how you are getting. So dv by dx is equal to c1 cos pi x by L. So x by L will be here multiplied. So d squared v by dx squared is equal to, again x by L will come. So first we will put c1 sine pi x by L. So here negative will be coming. So x by L will come. So it will become square. X by L the whole square. So when you put d cube v by dx squared, it will become, again sine will become cos. So x by L the whole cube c1 cos pi x by L. So d power 4 v by dx power 4. This time it will become x by L power 4 c1 sine pi x pi x. This negative will become positive now. So this is what we are going to put it here in place of the boundary condition d power 4 by dx squared. the d power 4 by dx power 4 by value is what, this is what we have got. So pi by 4, pi by l, x by, so pi by, this is pi, sorry, pi. So pi by l power 4, pi by l power 4, the C1, this constant is that sine pi x by l. So that is what. Minus q naught is already there in the field variable is already there in the differential equation. So here the domain value is not, it's in the previous case it's a 1 point solution, easy to find out. But here this domain residue is varying from point to point. So we can use the point collocation technique. We can say at particular point it is becoming zero and solve and we get the solution. So now we assume residue is equal to 0 at L is equal to L by 4. Total length is L. So at L by 4 we assume that the residue is becoming 0. So in that case, what will be the solution? That is what we are going to. Since this domain residue is varying from point to point. This domain residue is varying from point to point. It's better to go with this assumption of it is being converging residue be 0 at particular point around. So we take it as L by 4 alone, it will become 0. And in that case, we assume the value, we put the value of x is equal to L by 4 in the equation, in the residue we have got. Okay. In that case, we are able to get the value of C1, and the solution is what? This is the solution we got. So C1 value we are substituting in the trial. This is C1 value. Once we get the C1 value, the C1 value is what? When you substitute here, we got the trial solution for this solution. This is a solution for the problem. So this has come out because we have assumed that residue will become 0 at L by 4. When x is equal to L by 4, residue will become 0. So similarly, we can assume the problem different angle. That is when x is L by 3, x is equal to L by 3, it is residue will become 0. Residue will become 0. X is equal to L by 2, residue will be 0. These are all assumption you can make. Further assumption you can make. So further assumption we can make, and we can check how the solution goes. When you're taking the case, in that case, how the solution changes, you can find out. So now in that case, when we take different L by 2, L by 3, when I consume that the residue is becoming 0 at L by 2, L by 3 or L by 4, at all the places, the solution, how the solution respond is what we are getting. So you can see this is the strength of material solution. This is the strength of material solution. So I think L by 2 is very near to the coming near to the real solution. L by 2 is coming near to the real solution. L by 2, if you see this one, L by 3, yeah? L by 3. This is coming near to the real solution. So almost, but it's good that we are able to normalize the axial location of the beam, and we can see how the deflection varies with respect to the residual being 0 at different point. So this is a kind of a point collocation type. We are able to predict the beam in a simply support motion. So how the residual moves also. So normalize x location and residual, how the residual goes for all the type. So we can also try this with a two solution. Earlier we have taken only one trial solution. So this is a C naught C1 sine pi x by L. But this solution could be improved by including one more trial solution, C3 sine 3 pi x by L. Okay, in that case, how the in that case we will get two unknown, that is C1 and C3. This could be find out by equating the residues at L by 4 and L by 3 is equal to 0, and so we will get two equations. When you solve the two equations, we could find out the value of C1 and C3, and when you find the C1 and C3, our solution is ready for us. C1 and C3 value is ready. So two-term solution, you can compare the solution obtained by two-term. This is a strength of material, this is strength of material result, and this is two-term result. This is two-term. Based on two-term, this is the result we are getting. So we are able to ascertain how the solution moving near to the actual solution. We find out the approximation near to the actual solution in finite element. So more the complex, more variables in the unknowns in the trial solution, which is giving more accurate results. So residue at L by 4 and residue becoming 0 at 2 points, L4 and L3. In that case, you see the residual. In the previous case, when you take one single trial solution sine pi x by L, it will become residue will be becoming 0 at 1 point only. Here, when we are taking two trial solution sine pi x and sine 3 pi x by L, residue will become 0 at 2 points. Residue is becoming 0 at 2 points. So that is the advantage, and that's the reason for the solution being more accurate. So that's the evolution of the weighted residual method has come to formulate the mathematical differential equation. So weighted residual statement says like this: a weighing function into residue is equal to 0. So 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 rather we are trying to set a residual exactly to 0 at a few selected points. So we will not have a control over the residue at all. So or at the other points of the domain. So to minimize this kind of problems, we always introduce a weighted function with the residue, and this is good. It is giving a very good solution. So you can see this is the domain residue for the problem, and we assume the W of x, that is the according to the Gallatin's weighted procedure, we are including the weighing function here. So this will be a part of the residual that already we have formed. Already we have formed the residual, and residual function is actually based on the differential equation that is concerned to a domain, and this domain equation is derived for the particular field. Based on the particular field variable, we define the differential equation, and within that residual we take a function as the weighing function. That is what Gallatin's does, and this has given very good results, and many of the solutions computed with respect to the Gallatin's weighted residual has given solutions very near to the accurate results. So here we have got one constant, but according to Gallatin, 0 to L weighing function into the residual RD. So the weighing function into residual. So we choose one weighing function because there is only one constant. When we have more constant, we can use more W1, W2, W3. We can increase the weighing function. Okay. So we can integrate it and find out the value of C1 and substitute here, and we get the solution for the problem. So this way is a very good way to find out the solution. So now we do not worry about when the residue is becoming zero and what point we have to assume the residue to be zero. Doesn't mean. Now it is a constant weighing function is being integrated over the entire domain. So you can see the beam of a simply supported beam, and the same problem when you plot a graph between the strength of material result and the Gallatin solution method, and you can see this is overlapping and so accurate. Solution is coming very good. So actual residue in the Gallatin's method is coming this way, residual in the domain. So we can apply the Gallatin's weighted residual method for the heat transfer problem also. Here you can see a heat transfer problem, and this is the boundary conditions and the differential equation for the heat transfer problem. So heat generated is equal to heat lost. So that is given rise to this boundary condition. So assuming the trial solution, and we are finding the value of C1 and C2, and a domain is known. We introduce this. We minimize the residue, and find the solution. Even this problem of this varying load in a cantilever beam also can be solved by using the weighted residual method. Here, when you have more than one constant, as I told you, we use more weighing function and find the solution for this. So this is a rectangular plate subject to the uniform load, and you can see the governing equation. Since it is a rectangular plate problem, you have the partial functions coming into play, and the trial solution, we are assuming the triangular function, and weighing function, we are taking a weighing function inside the trial solution and integrating it, find the solution. And pin-fin problem also we are able to solve in a similar way. So comparing to the other methods, this Gallatin's method has given a good results. I hope you got a good idea of how a mathematical formulation could help you to solve real-time problems. And this is a starting point of any finite element mathematical formulation, which has paved the way for the software industry, that is CAD industry, to develop the software to a good extent. So,
thank you, Professor.
Yeah, yes, sir.
For your wonderful session.
Yeah, thank you, sir.
Thank you. Audience, participants, if you have any clarifications, you can ask your doubts.
So you can drop into my mail anytime, and if you have any queries in the presentation, I'm always ready to help you. If you have anything to ask now, you can also ask.
Dear participants, if you like to ask any query, you can post it on chat as well, so that I can read it out. Any questions regarding this session? You can actually unmute yourself and ask the questions, sir. Anyone?
Yes, I think we can wind the session.
Fine, sir. Thank you so much, sir, for your excellent.
Thank you. It's a nice being with you, and thank you, Mr. Dr. Murugan, and for inviting me to the session and being with you, discussing with you, and thank you all participants for listening me.
Thank you, Professor. Thank you very much for
Yeah.
your
Yes. Yes.
session. Wonderful
Yeah.
session
Yeah.
and wonderful time.
Yeah. Thank you.
Thank you.
Dear participants, the feedback link will be posted in some time. Just hold on. Sir Nyanakumar, sir. Sir, can you post the feedback link, sir?
So Jnana Kumar is not on the line, I think. Amos, sir.
Sir, yes, sir.
Then we'll give the feedback link and the next session.
Yeah, fine,
For
sir.
first and second, session,
Yeah,
we can
combine.
share the feedback separately.
Okay, okay, sir. Fine, sir.
Okay, sir. Thank
So
you.
we have come to the end of
Thank you.
the morning session. The next session will
Yes.
start 12 p.m. If I'm not wrong, yes, sir, 12 p.m. And we request you all to come back in the same link at 12 p.m. again. So thank you all for joining. See you at the 12 p.m. session. Thank you, sir.
Thank you, participants. Thank you.